So good morning students. Today we are going to discuss one of the chemical properties of amine, that is electrophilic substitution reaction in aniline. So what today we are discussing is electrophilic substitution reaction in aniline. Remember, electrophilic substitution reaction, halogenation, nitration, sulfonation and Friedel-Crafts reaction. So all the four we are going to do with aniline. First of all, we have to find out in aniline which are the positions which will be attacked by the electrophile. And you all of us know that there are three possibilities. Electrophile may attack at the second position, that's called ortho. It may attack at the third position called meta. It may attack at the fourth position, that is called para. So we have to find out at which position the electrophile on the aniline will attack. We will just prove it attacks at ortho and para. The NH2 group is an ortho-para directing group. Let's prove it. For that we need to draw the resonating structures. So let us draw the resonating structure of the aniline. Plus R effect. Nitrogen has a lone pair of electron. So just like phenol, anisole, aryl halide, the molecule will show plus R effect. So nitrogen gives electron to the benzene, and obviously if it gives electron to the benzene, it makes benzene electron rich. So what is going to happen, all of us know, the benzene will get attracted towards electrophile, or the benzene will get activated towards electrophilic substitution reaction. So we are just going to prove that aniline is going to undergo electrophilic substitution reaction at ortho and para position. And in aniline, the benzene ring is highly activated or dying to react with electrophile. Dying to react with electrophile. Like all of you are so activated towards the studies. All of you are such good children. Even in the lockdown you are studying. So you are activated towards the studies. And aniline is no exception. He or she, I don't know, whatever, is activated towards the electrophilic substitution reaction. So these are the 5 resonating structure that we have for the aniline. If you draw the hybrid, you will find the negative charge. You just take the average of all these structures, you will get the hybrid. This is the hybrid. All the bonds involved in the resonance, they will have a partial double bond, and the ortho and para positions will act as a negative center. So naturally electrophile will attack where there is a negative charge, because electrophile is something positive. So it will be attacking at ortho and para. So as I told you, in aniline, the electrophile will attack at ortho and para position in aniline. And secondly, since this group is giving electron to the benzene electrons becomes more, negative charge becomes more. So attraction towards electrophile will be more. So aniline is dying to react with electrophile. The ring is highly activated, as it will be evident as we do some reactions. So let us write these 2 points, that in aniline, electrophilic substitution reaction happens at ortho and para position, and secondly in aniline the benzene ring is dying to react with electrophile, highly activated ring, just like you. All of you are highly activated towards studies. So number 1, in aniline, all of you are such good children. So in aniline, the NH2 group shows plus R effect. The group is going to show plus R effect. Plus R effect. So due to resonance, what happens is ortho-para position, second and fourth position act as a negative center. So electrophile attacks on aniline on aniline at ortho position and para position. Second point, in aniline, since NH2 group shows plus R effect, so increases, there's a sign for increases electron density on benzene ring. It increases the electron density on the benzene ring, something negative increases on the benzene ring. So the benzene ring in aniline, dying to react with electrophile. Dye means activated. In aniline is activated towards electrophilic substitution reaction. Aniline is as activated as you are towards the studies, since all of you are good children. Now let us see the examples of electrophilic substitution reaction. So let us start with halogenation, then we do nitration, then we do sulfonation, and then we'll try to do Friedel-Crafts reaction, but you will find in aniline Friedel-Crafts reaction doesn't happen. We'll investigate why. So the first reaction of electrophilic substitution reaction, we are doing bromination. We can do any halogenation, we can do chlorination also, that is not an issue. So aniline, if you react with bromine, in aniline, as I told you so many times by now, the benzene ring is highly activated towards electrophilic substitution reaction. So when we do bromination, what happens is at all the ortho and para position, there is so much of negative charge. We don't have a mono substitution, we have a tri substitution, meaning by the Br plus will attack at this position, and this position simultaneously. So you will get the formation of 2,4,6 tribromoaniline. 2,4,6 tribromoaniline you will get. The ring is so much of activated. Ortho para positions have got so much of negative charge that the electrophile attacks at all the ortho and para positions simultaneously, and we get a tri-substituted product. Okay, like for example, we tell you to study and you attend all the classes starting from 10 o'clock in the morning till I think by 2:30 in the afternoon. You attend all the classes. Sometimes the science students, they even attend the commerce classes also, because they're highly activated towards the studies. Okay, they don't log out, they remain in the group even if they're not studying that particular subject or they don't have that particular subject in their course. So aniline is just like, it starts at one time and it reacts with electrophile at the 3 position. Now suppose somebody gives us a challenge. The challenge is we have to convert aniline into parabromoaniline. I don't want a tri substitution, I want a mono substitution. How do I go about? Now the problem is that we are getting a tri substitution because reason being the nitrogen gives lone pair towards benzene ring readily. The ability of nitrogen to give this lone pair to the benzene ring readily due to resonance. The ring gets too much of activated and it reacts with electrophile at all the 3 positions simultaneously. So if you want to get Br only at one position, you have to tell nitrogen not to give electron to the benzene due to resonance. But nitrogen will not obey. You must have heard in Hindi, लातों के भूत बातों से नहीं मारते. So nitrogen will not obey. Even if you tell nitrogen not to give electron to the benzene ring, it will give. Okay. So what I will do is that हमें nitrogen का कान खींचना पड़ेगा. What we'll do? Over here we are going to put a group. Over here, the group is going to be attached over here, which is going to pull away the electron of the nitrogen. So if that group is going to pull away the electron of the nitrogen, the ability of electron to go towards the ring will decrease and the activation will decrease. So let's see how do we pull the ear of the nitrogen. Ear means the lone pair of electron. How do we pull away the lone pair of electron of the nitrogen? So we have to convert aniline to parabromoaniline. So what we'll do, we'll take aniline. We will put over here a group that is acetyl group. I'll react aniline with a compound called acetic anhydride. We have used this in the preparation of aspirin also. So we're using acetic anhydride. What is going to happen? Acetylation reaction. The hydrogen will be replaced by acetyl group. We have discussed acylation in the last class. So we are basically doing acylation of aniline. Acidic hydrogen getting replaced by COR group, or specifically the COCH3 group over here. We are doing acetylation of aniline. So we can show this like this, double bond, or we can write it below so that it is visible. So we get acetylated aniline. The hydrogen will be replaced by the COCH3 group. This compound is called nothing but acetanilite. This is called acetanilite. Okay, or we can call it iopec. This is a common name. Iopec name will be N-phenyl ethanamide. N-phenyl ethanamide. Now what is going to happen? This CO group is going to pull away the electron of the nitrogen like this due to resonance. The electron will be pulled by the CO group like this due to resonance. So naturally, if these two electrons goes towards the CO group due to resonance, their ability to go towards the ring will be less, and with the result, activation of the ring will be less. Now if you do bromination, you will get particularly a major product, that is the para product. The Br will not be able to attack at the ortho position because a lot of steric hindrance is there. So we put it like this. We put a Br group at the para position, and now since the work is over, we have to remove this group. We can remove this group by adding an H+. If you add H+, the COCH3 group will go away. You will get a nice and clean product, that is para-bromoaniline. You will get plus the formation of acetic acid. So this was the first electrophilic substitution reaction in the case of aniline, that is bromination. Now let's discuss the next one, that is called nitration. In nitration also there is a panga. In aniline there is a lot of panga. At every step there is a panga. And aniline, the panga is because in aniline nitrogen has a lone pair of electron, and the ability of nitrogen to give lone pair of electron to the benzene is very, very high. Now let's see what happens in nitration. So when we do nitration, we expect that NO2 plus, the electrophile, will attack at ortho and para positions. We should get a mixture of ortho and para product. So see the magic of the thing. So if you have aniline, you do its nitration. आप इसकी nitration करिए. Conc HNO3, Conc H2O4, we have to add. We will get ortho product, quite expected. So NO2 at the ortho position. Very good. We will get the para product. इससे खुशी की बात क्या हो सकती है? So ortho and para product, but the magic begins. You will find para product will be 51%. 51 out of 100 molecules will become this. 2% molecule will be forming ortho. Now since all of you are very good in maths, 51 plus 2 is never 100, it is 53. What about the rest of the 47% molecule? Now here comes the catch. You will get also the formation of the 47%, the molecules which are not supposed to get formed. You will get meta-nitroaniline, and that too in 47% amount. Now we cannot say that this is formed by mistake, because you can't commit a mistake of such high magnitude. There must be some valid reason. And how do we avoid it? If you don't want the formation of meta-nitroaniline, how do we avoid it? So let us find out the reason why during the nitration of aniline we get meta-nitroaniline, and how do we avoid it? And that too we are getting how much of meta-nitroaniline? 47% amount. Not a joke. It's not by mistake. So we are discussing the question that why aniline on nitration forms 47% meta-nitroaniline. What is the story behind this? This is not a mistake. This is not a mistake. Now what happens when you do nitration of aniline? What we do? We take aniline. You will find the problem will be again due to the lone pair of electron on nitrogen. How do we do nitration? We use mixture of concentrated nitric acid, concentrated sulfuric acid. We are working in the acidic medium. Now what happens in an acidic medium? In acidic medium, I know it will come as a shock to you. The shock of your life. Be ready for the shock of your life. In acidic medium, the concentration of H plus is very high, or Pj. The concentration of H plus is very high. So what happens is during nitration, it is probability that 47% aniline molecule before nitration, before they undergo nitration, they are going to accept H plus because of the lone pair of electron on nitrogen. Nitration, they protonate. Protonate means accepting H plus. They will protonate. So we have aniline, and in aniline nitrogen has a lone pair of electrons, something negative. So before this can react with the electrophile NO2 plus, they will undergo protonation. H plus is going to attach on the nitrogen. So you get the protonated product, and this protonated product is called anilinium ion. So you get the formation of anilinium ion. Now you can see in anilinium ion, what is happening is we have a electron withdrawing group on the benzene ring. NH2 plus is electron withdrawing plus, so it will withdraw electron from the benzene. And now if it undergoes nitration, the attack will be at the meta position, because whenever an electron withdrawing group is there on the benzene ring, electrophile attacks at the meta position. So now after aniline undergoes protonation, it forms anilinium ion. Now it will undergo nitration, and when anilinium ion will undergo nitration, the NO2 plus will attack at the meta position. So let me write all this in words. The space is over, so I'm just rubbing off the above statements. I hope you have copied down the statements. Okay. So as I told you, what happens in anilinium ion, in nitration of aniline, 47% aniline molecule, before nitration they undergo protonation, and then what happens is anilinium ion has electron withdrawing group, EWG, electron withdrawing group, NH2 plus on the benzene. It has got NH2 plus group on the benzene. So anilinium ion reacts with NO2 plus, the electrophile in nitration, at meta position. And those aniline molecule which doesn't undergo protonation straight away reacts with the electrophile. They are going to give ortho and para product. Now let us see how do we avoid the formation of meta nitroaniline. Naturally, the problem is due to the lone pair of electron that is causing the problem. So you remove away the lone pair of electron, the problem will be solved. And you know how to remove away the lone pair of electron. We have just seen in bromination. How to avoid it? You take aniline, do the same reaction. You do its acetylation. You do know how do we do acetylation. We use acetic anhydride. The hydrogen of aniline is replaced by the acetyl group. Remember this compound? I gave you the name. It is called acetanilide. IUPAC name is N-phenyl ethanamide. Again, the lone pair will be attracted like this. The problem will be solved. Now you do its nitration. The main product that you will get will be, major amount will be the para one. Ortho will not be formed because of such a big group. Ortho attack will not be possible. So you get the formation of the para product, and then in the end you can remove this group. So NO2 now at the para position, put H plus, the group will get removed, the bond will break, and you will get majority of the product will be para nitroaniline plus acetic acid. The problem will be solved. So you can see in aniline, all problems creep in due to the lone pair of electron on the nitrogen. The problem doesn't end up over here. It will keep on happening in every reaction. The next reaction we need to discuss is called sulfonation. Let us discuss sulfonation of aniline. Sulfonation, which groups attach? The group that attaches is SO3H, sulfonation. So the problem is we take aniline, which is a Lewis base. Due to the lone pair of electron on nitrogen, we are reacting for sulfonation, we are reacting with an acid, concentrated sulfuric acid. So first of all, what is going to happen, you will get the formation of salt. This will give H plus, and the H plus will attach over here. You get the salt of aniline. Acid plus base gives you salt. You get the formation of the H over here, NH3 plus, and after giving H plus, this will become HSO4 minus. This is a salt. This is called anilinium hydrogen sulfate. Anilinium hydrogen sulfate. Now if you heat this anilinium hydrogen sulfate, it will rearrange itself into this compound, which is commonly called as nothing but sulfonelic acid. The common name of this compound. This is called sulfonelic acid. Sulfonelic acid. Can you try it, the IUPAC name of sulfonelic acid? Yeah, no problem. This is a preferred group. 1, 2, 3, 4. It will be called as nothing but 4-amino, NH2 acting as a substituent. And the rest of the compound is benzene sulfonic acid. So sulfonelic acid, the IUPAC name is 4-amino benzene sulfonic acid. Now the story doesn't end up over here. Sulfonelic acid is a very funny molecule. What's so fun about it? In the same molecule, we have got a basic group and we have an acidic group. This is a basic group and this is an acidic group. You know, we have an earth form. Earth form is such an organism which has got a male part as well as a female part in the same organism. So in this case, sulfonelic acid, what happened? There is a basic group and an acidic group. So what happens? Sulfonelic acid doesn't occur in this form. It occurs as a salt. Because the acidic and basic group present in the molecule, they can react with each other to convert into a salt. And since this salt, special salt formed by the reaction between acidic and basic group of the same molecule, it is called internal salt. So as I told you, this is a basic group because of the lone pair. This is an acidic group. This is can give out H plus. So what will happen? This will give H plus and this will accept H plus. So this molecule occurs in this form as a salt, internal salt. Why it is called internal salt? Because it is formed by a reaction between acidic and basic group within the same molecule. So H plus will attach over here. This will lose H plus, so it will become SO3 minus. And this is nothing but called internal salt. So sulfonelic acid exists as an internal salt. Technically, internal salts are also called as nothing but zwitterion. So sulfonelic acid exists as a zwitterion. So suppose somebody asks you what is a zwitterion, you will say this is internal salt. This is a internal salt. It is an internal salt formed. It is an internal salt formed in those molecules. Formed in those molecules. It is formed in those molecules which has both acidic and basic group. Both acidic as well as basic group. The one which has got both acidic as well as the basic group. Example you can give of this one, sulfonelic acid, exists in the form of a zwitterion. I can give you one more molecule which can form zwitterion. These are called amino acids, which have this formula, general formula. They have an acidic group, they have a basic group. Amino acid, you know, the one which forms the protein, the basic blocks of protein. So it has an acidic group, this is a basic group. These are called amino acid, AA. So what will happen? How does it exist? This will accept H plus, this will lose H plus. So it will become CO minus. This will become NH3 plus, and this is R. So even amino acid exists in the form of a zwitterion. So what is zwitterion? That is nothing but the internal salt. So we have seen when we do sulfonation of aniline, first of all we are going to get sulfonelic, the salt, anilinium hydrogen sulfate, which rearranges itself into nothing but sulfonelic acid, sulfonilic acid. Now let's do the last reaction for the day, that is called Friedel-Crafts reaction. And the magic is that in aniline, Friedel-Crafts reaction is not possible. Now you may wonder why Friedel-Crafts reaction is not possible. It's an electrophilic substitution reaction, and you only told us in the beginning of the class that aniline is dying to react with the electrophile. So then why on earth, if aniline is so much of activated, why it doesn't undergo Friedel-Crafts reaction, which is an example of electrophilic substitution reaction? I'll just tell you. So aniline, what happens if you react it with CH3Cl, catalyst, if you remember over here, that will be the major problem that will be creating anhydrous AlCl3, the Lewis acid, electron hungry compound. Aluminium octet is not complete, aluminium having only 6 electrons in their outermost shell. So when you react aniline with alkyl halide anhydrous AlCl3, answer will be no reaction. And we have to investigate why, when the aniline is so much of activated, why doesn't it undergo Friedel-Crafts alkylation and acylation? What's the problem with aniline? So the question we are discussing, the last question for the day, that why aniline doesn't undergo Friedel-Crafts reaction. Why it doesn't undergo Friedel-Crafts reaction. Now the problem is that when you mix aniline, when we mix aniline, alkyl halide and the catalyst anhydrous AlCl3 to do the reaction, what is going to happen? Aniline, which is a Lewis base. This is the fourth time I'm telling you why aniline is a Lewis base, as it has a lone pair of electron on the nitrogen. So aniline, which is a Lewis base, will form a salt. In fact, it is going to react with a catalyst. Catalyst is not supposed to react with a reactant. This is supposed to facilitate the reaction between these two compounds. But what happens, instead of this reacting with this is going to react with the catalyst, because this is a Lewis base, this is a Lewis acid. So Lewis base, that is aniline, will form a salt with a catalyst. The catalyst we are using is nothing but anhydrous AlCl3. So instead of aniline undergoing reaction with Rx or CH3Cl, it reacts with nothing but a catalyst. It reacts with a catalyst. So we have NH2, lone pair. This is AlCl3, electron deficient compound. This is a Lewis base. This is a Lewis acid. So it gives electron to the AlCl3 and it forms coordinate covalent bond. As it gives electron to AlCl3, the nitrogen will get a positive charge. And this positive charge group is going to deactivate the benzene ring towards electrophilic substitution reaction. N will get a positive charge. It becomes an electron withdrawing group. And with the result, it will deactivate the benzene ring towards the reaction with CH3Cl. So what happens? I have written aniline, Rx, that is alkyl halide, and anhydrous AlCl3. When mixed, what happens is aniline, Lewis base, will form salt with catalyst anhydrous AlCl3, which is a Lewis acid, which is La, not Los Angeles, it's Lewis acid, and it forms a salt. And then you say that in salt, the nitrogen of aniline has a positive charge, and with the result what happens? And it deactivates the benzene ring. It deactivates the benzene ring towards Friedel-Crafts reaction. It will deactivate the benzene ring towards Friedel-Crafts reaction, alkylation as well as nothing but acylation. So aniline, because of the Lewis basic nature, doesn't undergo react with Friedel-Crafts reaction. You can see in every electrophilic substitution reaction, the problem which happens is due to the lone pair of electron on nitrogen in the case of aniline. So in today's class, we'll discuss electrophilic substitution reaction of aniline. In tomorrow's class, we'll discuss the last property of amines, that is the basic nature of amines. Till now, till then, take care. Have a nice day. Thank you. Bye.